In this first lesson, there are two big ideas. One, limits, two, continuity. And our goals in this first lesson is to walk away understanding what a limit is, so therefore its definition, and what it means for a function to be continuous. And we will explore some discontinuities that you probably learned about in Algebra 2, as well as the definition of continuity. So first, consider this piecewise function f of x. So remember, a piecewise defined function, sometimes I will abbreviate that, piecewise defined function. A piecewise defined function is a function with, well, different pieces over different subintervals of the real number system. So if we consider the first part of this function, we know that f of x is going to be this rational function, 4x minus 8 over the difference x squared minus 4. And that's going to be our function for all values of x that are less than 5. So on our number line, and I am going to go back and erase some of this highlighting, but on our number line, from where x is 5 and all the way to the left, we could see that we have this rational function. And then at 5, at x equals 5, we could see that our function becomes linear. So for values of x greater than or equal to 5, our function is this line. And we can also see that there's that closed circle. So where x is greater than or equal to 5, from the graph, we know the value of f of 5 by looking at that closed circle. From the function, we know that we would use this piece of our piecewise. Okay, so the first task that we're going to do is to just evaluate f of 2, f of 9, and f of 5. And again, we want to practice doing this from the graph, but also using the function itself. So if I go to the graph, I notice that when x equals 2, so remember, if this is f of 2, this is our input where x is equal to 2, I notice that at 2, there is an open circle right there, and nowhere above or below do I see a point on where x is 2. So I can tell from the graph that f of 2 does not exist, or we could say is non-existent. Now, if I were using the function, the piecewise function, I know that I would use the top piece to evaluate f of 2 because 2 is an x value that is less than 5. So if I were using the top piece to evaluate f of 2 would be, well, let's see, 4 times 2 minus 8 over 2 squared minus 4. And that gives me 0 over 0. So we know in math that something weird happens when we divide by 0. So I can tell that when I get a number divided by 0, well, that's going to result in something in our graph. And we'll find out later in this lesson exactly what that is. So one way or another, f of 2 is non-existent. All right, so next, if we are evaluating f of 9, oops, sorry, trying to choose a different pen color here. If we're evaluating f of 9, using the graph, I can see, okay, x equals 9 is right here. It appears that f of 9 is 1. So just double check using our function. Well, since 9 is a number that's greater than or equal to 5, well, greater than, we know it's not equal to 5, I would use the bottom piece of the piecewise. So 10 minus 9 would yield 1. Okay, so f of 9 is equal to 1. And then finally, we're asked to evaluate f of 5. And we alluded to this earlier, but 5 is what we call the boundary of this piecewise. So at x equals 5, that's where our function changes from a rational to a linear function. So I have to be really careful that I look at the boundary of my piecewise. I'm going to still use this bottom piece to evaluate f of 5 because 5 is greater than or equal to 5. 5 is not less than 5. So I could write f of 5 is 10 minus 5, which is 5. And again, when I go to my graph, I could see right here, well, that's f of 5. Had I used the bottom piece, or excuse me, the top piece of the piecewise, I would have gotten some number between 0 and 1 right here where that open circle is, but that would not be correct. So when we evaluate, we want to make sure that we are finding the value of, in this case, our function f for some particular input, and we'll be able to do that from a graph, from a function, etc. Okay, so when we talk about the behavior of a function as we're approaching a value, what we're really talking about is a limit. And so to be clear, a limit is not necessarily the value of a function. It can be. But when we look at where our function is, like what happens as we approach, as we get really, really, really close to a particular value, that's when we're talking about a limit. And I'm so sorry, you're going to notice sometimes this funny box right here. That is just an issue with Microsoft Word. That should print for you as the real number symbol. And we'll come back to that in just a second. So, okay, so as we look at this idea of a limit, the definition of a limit is that if f is a function, and as I read this, we'll get used to this notation. I know it looks like a lot at first, but we would read this as a is an element of the real number system, or the set of real numbers. I'm going to say the set of real numbers. So this is a little set builder notation. We'll just see it a lot. It'll be okay. All right, so f is a function, and a is an element of the set of real numbers. That just means that a is any real number, any number in the real number system. So we're given the definition of the limit, that the limit of f as x approaches a is equal to L if and only if. And then we're going to read this carefully because I want you to notice there's a minus and a plus sign here. So this first piece is going to say the limit of f as x approaches a from the left. So that teeny little negative sign that is after the a, not before the a, means we're approaching a from the left. That if that is equal to the limit as x approaches a from the right of f, so again, this little plus sign here, oh, sorry, I have this toolbar up here I'm trying to drag out of view. This little plus sign here indicates that we're approaching the function from, we're approaching the value a from the right of the number line. If those two, what we call one-sided limits, are equal, then the limit of f as x approaches a exists. And its value is this capital L. So that L is just the limit. Now, that's a lot to read. So we're going to understand that in just a moment by going back and looking at our graph. Often you'll find in these spirals that often the notes that are under the box are just important as, if not more important than what's in the box. So it is important to note that if the limit from the left and the limit from the right are not equal, they do not agree, then we say the limit is non-existent. So we could still describe the function as having a limit from the left or the right, but if they're not equal, the limit does not exist. Okay, so going back to our original function, we're just going to look at this graphically for a moment. So we're asked to evaluate the limit of f as x approaches -2 from the right. So I'm looking at this first limit. So as I go to my graph up here, I see where x equals -2. And if I'm approaching that from the right, that really means that I'm like at this part of the graph. So I'm going kind of backwards. I know we read left to right, so it's kind of funny to look at it this way, but I'm coming at -2 from x values that are to the right of -2 in the number line, such as -1, 0. Although technically we want to get really close. So like -1.99999 and so on. So I could see that there is a vertical asymptote here at x equals -2, but the graph itself, the function itself, is approaching infinity. So there are two things that we could say here, and I'm going to encourage you to say the thing that is more specific. So from the right, the limit, and I want you to practice this limit notation. I'll tell you, AP, the College Board, when we write our free response questions, they are very picky that we do this correctly. So the limit of f as x approaches -2 from the right, we want all of that to be under the LIM of limit. We could say that that's going to infinity. I try not to use an equal sign when I write infinity. I'm going to do it anyways right now because infinity is not a value, so you can't equal infinity. But the other thing that we could say here, so this is the more specific thing, that our limit is approaching positive infinity. That graph is going up forever from the right. But we could also say that the limit does not exist or is non-existent, because anytime our graph is approaching infinity, it's unbound. So like there's no limit, there's no like maximum or minimum y value where we like top off, or no particular y value, I should say. We're either going up to infinity or going down towards negative infinity, and those aren't values, so the limit is non-existent. All right, so that was as we were approaching -2 from the right. The next limit that we're going to evaluate is the limit as x approaches 2 of f. So we're approaching +2. All right, so I'm going to go back to my graph. Oh, and now I'm like, wait a minute, something funny is happening at 2. So we already said that f of 2 is undefined. So f of 2 is non-existent. However, it is possible for the function value to be non-existent and the limit to exist. So as I approach 2, and again, I'm looking at the graph itself, as I approach 2 from the left, so from x values that are less than 2, and as I approach 2 from the right, so from x values that are greater than 2, I notice that from both sides, the graph is going to the y value where that hole is, where that open circle is. We will learn that is definitely called a hole. So even though f of 2 does not exist, the limit of f as x approaches 2 does, and it's 1. So it's the y value where that function was headed. That graph was headed for an output of 1. Okay, so we would say the limit as x approaches 2 of f of x equals 1. All right, and again, we have to check both sides. So coming back up to this note, if one of those sides did not agree with the other, then the limit would not exist. All right, finally, the limit of f as x approaches 5. So as I go up to my graph again, I remember 5 was the boundary of my piecewise, so there was something interesting happening here anyways. So as we approach 5 from the left, I notice that this kind of rational piece, we said before, this was headed towards some output, some y value between 0 and 1. However, if I approach 5 from the right, I'm now using the other piece of my piecewise, and I notice that that value is 5, that our output is the y value 5. So the left-hand, or the left-sided and the right-sided limits exist separately. I don't know exactly what the one from the left is. We would just have to plug it into the piecewise. But the limit itself does not exist, because going back to this idea of a limit, the limit exists when from the left and the right, the function's headed to the same value. Here, our output's headed to like 0 point something. From the right, our output is headed to 5. So all of that to say, the limit of f as x approaches 5, I could say is non-existent, or we could say does not exist. I don't know that it's a great practice, but occasionally I will write DNE to abbreviate does not exist. But to really drill in the reason for this, the reason the limit does not exist is what is written in this note under the box, that the limit of our function f as x approaches 5 from the left-hand side is not equal to our limit of our function f as x approaches 5 from the right-hand side. And sometimes we will have to write that. Like sometimes we will have to give a justification in a free response question as to why something is not continuous or as to why a limit does not exist. So I think it's important that we just familiarize ourselves with that reasoning and that notation. All right, finally, we're going to talk discontinuities. And we're going to talk about this and continue on the next page. So in Algebra 2, you learn about different types of discontinuities. And as a reminder, there are 3 discontinuities. So a really informal definition that and let me back up. I don't even want to use the word definition. I'm going to say an informal understanding of these discontinuities is that if you have to pick up your pencil when tracing the graph, there's a discontinuity. I want to stress that that is not the definition of continuity or discontinuity, and that's going to be really important. So there are 3 types of discontinuities that we're going to learn about. One of them is a vertical asymptote. So a function has a vertical asymptote at a particular value of x. So I'm going to say at x equals a, where a is just a number, if f of a is equal to a number over 0. So not 0 over 0, but a number over 0. So for example, like if f of a was equal to like 7 over 0, I would know that I have a vertical asymptote there. So as we look back up at our graph, I know I'm scrolling up and down a lot on this page, sorry, and I keep erasing what I doodled on the graph. As we look at the graph, at x equals -2, there is a vertical asymptote there. So I could see that, and we know rational functions, we're going to see vertical asymptotes. So I could see this like lower piece of my rational function is approaching that asymptote. Then we're also approaching the asymptote on the other side, but we are not going to cross that asymptote. So if I were to, we're seeing this happen at -2, well, let's see why. So as I use the top piece of my piecewise, if I were trying to evaluate f of -2, I know I would use the top piece because -2 is less than 5. So 4 times -2 minus 8 over -2 squared minus 4. Well, that's what? -8 minus 8. So we get -16 over 0. So without even seeing the graph, I can determine that x equals -2 is a location of a vertical asymptote by using the piecewise defined function and observing that f of -2 yields a number divided by 0, not 0 divided by 0. So let's talk about 0 divided by 0. When that happens, we have a different scenario. We have a hole in our graph. So a function has a hole at some particular value of x. So again, x equals a. If and only if, when we evaluate the function, we get 0 over 0. So the big difference when we're looking at a function and we're analyzing it without the graph, the way we could tell the difference between a vertical asymptote and a hole is, do we evaluate and get a number divided by 0, or do we get 0 divided by 0? So this graph has a hole in it, and the hole occurs at x equals 2. So we said that this was the location of our vertical asymptote at x equals -2. We have a hole at x equals 2. We're going to talk about x equals 5 in a second, but I'm going to tell you that is not a hole. All right, so we have a hole at x equals 2. And again, like we kind of already did this down here, when we went to evaluate f of 2 and we said it was non-existent, what happens is when we plugged in 2 for x, we got 0 over 0. So without looking at the graph, this 0 over 0 is the indication that there is a hole when x is equal to 2. All right, finally, the last type of discontinuity, oops, I went too far, that we're going to talk about, well, the only other type that we're going to talk about is what we call a jump. And sometimes I notice sometimes students want to confuse jumps and holes a little bit. So here's the thing, a jump only happens when we have a piecewise defined function. And in fact, a jump can only happen at the boundary of a piecewise defined function. However, a piecewise defined function could also be continuous at its boundary. So I'm sure we'll see that down the road. So a jump, we will know that we have a jump if the limit of our function, and again, we're looking at a piecewise defined function, if the limit of f as x approaches some particular value from the left is not equal to the limit of f as we approach that same value from the right. So going back to our graph, we do have a jump at x equals 5, and we alluded to this before, but the reason for our jump, oops, I'm trying to pick a color that will show up on the graph, is that the limit from the left, so we said the limit of f as x approaches 5 from the left is like somewhere between 0 and 1. I'm looking at this output. Here's 1, here's 0, somewhere in there. And the limit from the right as we approach 5 is the number 5. So because those are not equal, that's how we know that we have a jump at x equals 5. And again, we said that 5 is the boundary of our piecewise defined function. Piecewise defined functions can have more than one boundary. It just depends on how many pieces they have. This one only had 2 different pieces, and the boundary is at 5. Okay, we are going to continue our conversation about continuity on the next page. So this should be page 2 in your spiral. And earlier I said that if you have to pick up your pencil to graph, like to trace the graph. So for example, if I go back up, sorry, I told you to turn to page 2. I'm going back to page 1. Sorry. But like if I were trying to graph this and I had to get over that vertical asymptote, I have to lift my pen or pencil to do that. So same thing here. I get to this hole, I have to like scooch over, lift my pencil. I get to this jump, I have to scooch all the way up here, lift my pen or pencil to trace that. So I cannot stress enough, that is not the definition of of continuity or a discontinuity. We have a very formal definition, and I'm just going to tell you right now that it's going to be very important for our work this year that we know this definition inside and out. And I'm actually going to write a version of it that's not written in this box right here. Okay, so if we don't have a discontinuity, if our function does not have a discontinuity at x equals a, so just some particular value of x, we say that our function f is continuous at x equals a. Functions could also more generally be continuous everywhere. So for example, the function x squared, just the quadratic parent function, that's a function that's continuous everywhere, right? It's a parabola. It has no holes, no jumps, no vertical asymptotes, and it's continuous across its domain of all real numbers. So we know it's continuous at any particular value of x as well. Okay, so the definition of continuity is this, that a function is continuous at x equals a if the limit of the function of f as x approaches a is equal to f of a. So the limit must exist, f of a must exist, and they must be equal. Now, the way that I prefer to write this, because I think more often than not, like this might be more helpful, is that we already said the definition of a limit is that the limit of f as x approaches a from the left is equal to the limit of f as x approaches a from the right, that must also be equal to f of a. So these two statements are the same. I just, instead of writing this as just the limit, I broke it out into the two one-sided limits over here. So I personally kind of like thinking about all three of these things must be the same. As we approach a from the left, that limit must equal the limit as we approach a from the right, and then the function must exist there and it must have the same value. So when I say the definition of continuity, I mean these two statements, what is in the box right here and what I wrote out right here, which is just kind of a more specific or longer version of that. I don't even mean in words. I don't mean talking about picking up our pen and pencil. And again, this is important because in our free response questions throughout this year, we are going to have to provide a mathematical justification for why something is or is not continuous, and we need to know this. So I'll just go ahead and tell you anything in a box you want to memorize one way or another. So, all right, I'm sorry, my phone's behind me and it's not on silent. Okay, so we talked about our particular definition of continuity. So let's move on to an example. So if f is continuous, we got that set notation again. So if f is continuous for every x that is an element of the set of numbers from x equals a to x equals b, or the closed interval a to b, then we say f is continuous on the closed interval a to b. If f and g are both continuous functions, then these things are true. So like f plus or minus g is continuous, f times g is continuous, f divided by g is continuous, and f composed of g is continuous. We're going to come back to that in just a moment. So let's take a look at this first example. The graph of g is shown below, and we're going to use the graph of g to answer the following questions. So identify the location and type of each discontinuity. Justify your answers using the definition of continuity. So as I start from the left, as I just kind of trace my graph, the first thing that I see that happens is that x equals -4. And so of our three discontinuities, that is a hole. So we would say that g has a hole at x equals -4. And when we go to justify our answer using the definition of continuity, to prove that something is not continuous is going to be easier than to prove it is. We just have to prove that like one of these three things is not true. Like either the limits don't match, or the function value is not equal to them, or the limit or the function value are non-existent. So I can't really talk about the limits here. The limit of g as x approaches -4 exists. It's 2. It's that number that we would expect to see filled in right there. But what I can say is that f of -4 is non-existent. I cannot say the limit is non-existent because the limit exists. But f of -4 is non-existent, or f of -4 does not exist. That's why our function is not continuous at x equals -4. Okay, so as we move across, we get to our next discontinuity, and that's going to happen at x equals -1. And again, this is what we call a jump discontinuity. It's not a hole discontinuity. Going back to this hole right here, at a hole, the limit always exists. So like our function was approaching that hole from the left and right. At a jump, the limit from the left and right don't agree. So I could see that we have a jump discontinuity. We can just kind of observe that. So I would say that g has a jump at x equals -1. And when I go to justify it, I can't use the same justification. I can't say g of -1 doesn't exist, because g of -1 does exist. It's whatever that output is where the closed circle is. But what I could say is that the limit, oh, you know what? This function is named g, and I called it f over here. I just caught myself doing that. That is bad form. Okay, my name starts with a G, and I would not like it if we misspelled it with an F. So, okay, so my limit of g of x as x approaches -1 from the left-hand side is not equal to my limit of g of x as x approaches -1 from the right-hand side. So that is our very specific reason. You could also say that the limit of g of x as x approaches -1 does not exist or is non-existent. I prefer the first reason because it tells us a little more about like what's actually happening there. When we say the limit of g as x approaches -1 non-existent, that could mean that we have like a vertical asymptote. So I like to kind of give the more specific reason when I can. All right, finally, speaking of vertical asymptotes, we do have one more discontinuity, and that is going to happen at 2. So if I were tracing my graph on the other side of that jump, I would be like, oh, it's down here. Whoop, now it's up here. So that means at x equals 2, we've got a discontinuity, and that, again, is a vertical asymptote. So I'm going to abbreviate that VA at x equals 2. And again, we could give several different reasons for why there's a discontinuity. It just has to be true. So I could say like g of 2 is non-existent. That's true. I could say the limit of g as x approaches 2 is non-existent. That's true. You know, there's a lot of different ways we could write it. So as long as we provide a justification as to why this statement is not true, we've proved that our function's not continuous there. Okay, so what I would love for you to do is pause the video real fast, evaluate these 4 limits below, and then unpause the video to check them. All right, so the limit of g as x approaches -4. We're asked to use the graph to evaluate that. So as I look at my graph, as I approach -4, we have a hole there. Our limit exists. Our limit is the value we're expecting to see where the hole is. Because remember, a limit is not the function value. The limit is where the function is headed. And as we approach -4 from the left and the right, our function's headed to 2. It just doesn't get there. All right, the limit of g as x approaches -1. Well, we actually talked about this one already. This is non-existent. I'm going to write D and E for space here, but for the reason above, referring to this jump, our limit is non-existent. All right, the limit of g as x approaches 5. Well, if I look at where x is 5, our function's continuous there. And so by the definition of continuity, if my function's continuous, then the limit value is equal to the function value. So, or I could just see with my eyes that the graph is headed towards 3. So g of 5 is equal to 3, and the limit of g as x approaches 5 is also equal to 3. All right, finally, we got to be careful with this little plus sign, the limit of g as x approaches 2 from the right. So that's where our vertical asymptote was. If we're approaching 2 from the right-hand side of 2 on the number line, so like coming from the number 3, headed backwards towards 2, I could see that this graph is going to go up, up, up forever. So the most specific thing that I could say there is that we're approaching positive infinity. You don't have to write the positive sign, but if it were negative infinity, we'd write the negative sign. So I could also say that the limit is non-existent, but anytime I can describe more specifically what's happening there, I really want to do that. Okay, so we practiced using, describing discontinuities using a graph. What is a little harder is describing our discontinuities using the function, like by function analysis, but that's a really important part of what we're going to do in this first unit. So if we look at this first example, we are asked to consider the function f of x and to identify the location and the type of each discontinuity. So remember, there are only 3 discontinuities. I'm going to go back to the last page for just a moment. We said a jump only happens at the boundary of a piecewise function. And f of x is not a piecewise function. So then when we consider a hole or a vertical asymptote, both of these discontinuities happen when our denominator, so the bottom of our rational expression or whatever type of expression when our denominator is 0. So unless we have a piecewise function, we don't have to worry about a jump. So all I really care about is what would make my denominator of f of x equal to 0. So I'm going to check. I'm going to start by setting my denominator equal to 0. I'm going to solve for x. I'm going to factor this. It's a difference of squares. You could alternately add 9 to both sides, but if you add 9 to both sides, be careful. We get two solutions. You get negative and positive 3. You don't have to write the plus sign for another 3. So if you solve it this way, just keep in mind if you add 9, you get x squared equals 9. When we are solving a quadratic, we need to consider both the positive and the negative square root of 9. So positive and negative 3. Okay, so that's the location of two discontinuities. The question is, what type are they? Well, let's check. So one at a time. Let's start with negative 3. If I try to evaluate f at negative 3, I get 3 minus negative 3 over negative 3 squared minus 9, which we already know is 0. And so we get 6 over 0. So again, because we get a number over 0, not 0, well, 0 is a number, so I shouldn't say that. We get a non-zero number over 0. That's how we know that we have a vertical asymptote at x equals negative 3. So it's the fact that the negative 3 makes the numerator a non-zero number, but the denominator 0. All right, so if we were going back to do the same for positive 3, f of positive 3 is 3 minus 3 over 3 squared minus 9. That's going to yield 0 over 0. That's how we know there is a whole. So it's really important that we keep those straight. I get they're easy to mix up. We just got to own it. We got to know that. All right, last example on this page, and then we'll talk about the intermediate value theorem on the next page. We're given this function h. We're asked to evaluate each of the indicated limits. Now, I can tell just with my Algebra 2 knowledge that this is a quadratic function h. Quadratic functions are continuous functions. So because this function is continuous, remember the definition of continuity, I'm going to abbreviate that, the DOC. The definition of continuity tells us that the limit of, I'm going to use h because our function is h, as x approaches some particular value is equal to our function h at that value. And so we know this is a continuous function. If we didn't know that, if we're not feeling confident about that, think of it this way. It's not piecewise, so there's no potential for a jump, and it doesn't have a denominator. So there's no potential for it to be a number divided by 0. So this is just a continuous function h. All right, so if I want to evaluate my limit of h of x as x approaches 3, well, that's just going to be the same as h of 3. So let's evaluate h of 3. We get 3 times 3 squared plus 2 times 3, which is what? 27 plus 6? We get 33. So therefore, that is equal to the limit of h as x approaches 3. All right, same thing down here. If we're evaluating the limit of h as x approaches 1, that's going to be equal to h of 1 because this function is continuous. So h of 1 is just 3 times 1 squared plus 2 times 1, and that is 5. 3 plus 2 is 5. All right. The last thing we're going to talk about is the intermediate value theorem. I'm going to make a separate video for that just so this one doesn't run super long.